Okay, now we get to look at how our conic sections are applied in real life, and we're going to start with ellipses and applications of ellipses. So if you look at the first sheet that I provided, here are some kind of fun ones. The football, the shape of a football is based off of an ellipse, as is the Batman symbol. So that's really important to us. Other applications are bridges that they build. If you look at that handout, or the first picture that I gave you, that is a picture that I took when we were on vacation. I think that's from a place in Pennsylvania, but it's an construction. They construct building and bridges using the shape of ellipse. Also, the orbits of planets are based off of ellipse many times, and we use that for space applications. And then a medical application, which would become really important if you ever had a kidney stone, is a lithotripter. It's a device that uses that they use to crush kidney stones, and so we're going to be doing. That's one of the examples we'll be looking at. So there's lots of good applications in everyday life. So the first one on our sheet we're going to do is this picture of an arch bridge. It's a double one. It says, in some cases, bridges are built using uniform elliptical arch bridges as shown in the figure given. Find the equation of the ellipse forming each arch if it has a total width of 30 feet and a maximum center height of 8 feet above ground level. The height of, and then it asks us a question. We'll deal with the question in a minute. Oh, there was another picture that I provided for you guys, and that is a picture I took. I think we were in Tennessee, where they just had built a, maybe the Smoky Mountains, they had built there's lots of tunnels through the mountains, and so that one was based off an ellipse, or perhaps a parabola as well. Okay, so let's deal with this. First, what we're going to do first is look at what they gave us and write the equation of an ellipse. Now, this is a double arch bridge. We don't have to look at both of them. We can just simply consider one of them and get an equation for one of them in order to answer the question they're asking us. So what's happening here is this is above ground. So since this is based on an ellipse, the other part of it is, we think about it, this is going to be below ground. So this is what the rest of this guy would look like. It would look like this. Okay, that's going from bad to worse. Let me try harder. Maybe like this. That doesn't even look that good, but there it is. That would be the underground part of this ellipse. And so we have a choice when we have a problem like this. We get to choose where we want to center it. The very best choice is to center it at the origin, because that's easiest. So let's do that. This is our picture, and I'm going to choose to center this guy at the origin. So I'm just going to place an axis on top of this so I can talk about that. So that means from the center to the top of this part of the ellipse is 8, okay? And from the center to this bottom part, even though my ellipse doesn't look symmetrical, I'll try to make it look a little bit better. Okay, this is also 8 from here to here, here. Okay, now it said that this total distance is 60, but it said the width of one is 30. So half of 30, that means it's 15 on this side and 15 on this side. So we can write the equation of an ellipse. It's going to be x squared over a squared plus y squared over b squared is equal to 1. Because I chose to center it at the origin, I get this simple formula. A is always the horizontal distance, so this is 15 squared. B is always the vertical distance, so this is 8 squared. So this is an equation that describes this ellipse. So if I go ahead and square that, that's x squared over 225 plus y squared over 64 is equal to 1. All right, that's the equation of the ellipse that this bridge is based off of. Now, they ask us the question, what is the height of a point 9 feet to the right of the center of each arch? What is the height of a point 9 feet to the right? So let's go out here, 9 feet to the right. I'm just decided to look at this guy. So if I go over about 9 feet, I'll say that this is 9 feet from the center, because all the way here is 15. And if I go up here, how high is this? This is how high, that's what I want to know. How high is this reaching? Okay. So what they tell me, if I go 9 feet to the right, here. Let's consider this point. This has the coordinates, x is going to be 9, and y is going to be, we don't know. How can we figure out that height? Well, we have this awesome formula we just came up with that describes every point on this ellipse, and the point we're interested is in this one. So let's plug in the x value, 9, and solve for y. So if we did that, 9 squared is 81 over 225 plus y squared over 64 is 1. We're just solving this equation. I'm going to subtract 81 over 225. I'm going to make my 1 look like 225 divided by 225. That is another version of 1. And why that is helpful is now I can subtract my fraction. So 225 minus 81 is equal to, what is that equal to? 144 is what it equals to. So this is 144 over 225. And now if you have a fraction equals a fraction, and I do, I'm going to cross multiply here. 225 times y squared is equal to 64 times 144. To solve for y squared, I'll divide both sides by 225. And I get that y squared is equal to some big number like 40.96. And then I take the square root, and I only keep the positive one because it's height, and that's what we're dealing with. And it's 6.4 feet. So if we needed to write a sentence here, we would say the height of the bridge (9 feet to the right of the center) is 6.4 feet. Why would we care about the height 9 feet wide? Oh, because of this. Trucks and big heavy things will be driving through there, and we only want to let trucks through on that road that are not going to break the bridge and cause some kind of collapse. So that's why we care about things like that. Okay, let's do the lithotripter. This is a good application right here. I have a little picture on your sheet, so let's just read about it. It says an application for medicine is a lithotripter, a machine used to crush kidney stones via shock waves. The patient is placed in an elliptical tub with the kidney stone at one focus of the ellipse. A beam is projected from the other focus to the tub so that it reflects to hit the kidney stone and crush it and get that patient out of all the pain that they're in. So there's a little picture. The picture that shows up on your sheet does not go with the problem. It's got different numbers, but it gives you an image of how they would do that. It's kind of like, here is our ellipse, and at one focus is like the source of the shock waves, and the other is the kidney stone. Okay, so here's our problem. It says a patient's kidney stone is placed 10 units away from the source of the shock waves of a lithotripter. Okay, so the key to knowing this is to know that at one point is the kidney stone, and at the other point of is the shock waves. These are placed at the foci, so that's a big deal to know that. So what they're saying in our particular problem is that they're 10 units away from each other. So that's 10 units away. So what I'm going to do is I'm just going to borrow this little image that I've got, and let's just make this, I'm going to center this at the origin because that's the easiest thing to do. So if from here to here is 10, then from here to here is 5. And so what I know is that C is 5 because C is the distance to each foci. All right. Now whether I chose to orient this horizontally or vertically, it doesn't matter. I just picked one. Then it says the lithotripter is based on an ellipse with a minor axis of 8 units. That's the shorter axis. Well, since I have chosen to put the foci on the horizontal axis, then that means the vertical axis is the minor axis. And so if its total length is 8, from here to here is 8, then that means that this is 4 and this is 4. So that means B is 4. Okay. Then, what else do we need to know? B is 4. Find an equation of an ellipse that would satisfy the situation. So, there's more than one, but here's one that would satisfy it. If I chose to center it at the start, x squared at the center, x squared over at the origin is what I'm trying to say. X squared over a squared plus y squared over b squared is 1 will be the equation of my ellipse. Okay, so what is the value of a? I don't know, but I know b is 4, so I know 16 goes here. And I know how a, b, and c relate. C squared is equal to the absolute value of a squared minus b squared, or the bigger value minus the smaller value. The way I've drawn mine, the bigger value is a, so it's going to be a squared minus b squared. C squared is going to be, c squared is 25. It's going to be a squared minus b squared, which is going to be 16. So a squared is going to be 25 plus 16 is 30, 41. So a squared is 41. This is the equation of an ellipse. This is one that would work. Now, I did this problem where I decided to orient it vertically, and the equation that I came up with was x squared over 16 plus y squared over 41 is 1. This is also a good equation. There are others that would do this. You would not have to center it at the origin. You could center it at any point. And so there's an infinitely many correct answers to this based on where you decide to center it, or if you want to orient it vertically or horizontally. Okay, that's that one. Let's do one. Let's introduce parabola, applications to parabolas. And so if you look at that sheet, I have a picture on there of a flashlight, and I have a picture of satellite dishes, and then there is a picture from Socorro, New Mexico of the Very Large Array, and lots of times that appears in alien films. When they're saying, are we getting signals from outer space, they'll show a shot of that Very Large Array. So let me see, I think I have other applications of parabolas are parabolic dishes are used for microphones a lot of times, and for any kind of receiving signals. Bridges are also based on parabolic curves sometimes as well. So the flashlight is interesting, and I just want to read this straight so that I don't mess it up. Where's my little flashlight one where it talks about that? It has to do with how you make the light beams point in a focused direction. If you did not base it off a parabola and point them towards the focus, then they would all be like a wad of light that wouldn't help you see anything. But when they all point the same way, that makes a beam of light, and that's what makes a flashlight useful. And so this is how they say it. Let me see. It's the parabolic reflector in a flashlight concentrates the light emitted by the bulb located at the focus. And so what that basically does is it concentrates it so that they all point the same direction, and it makes it useful. Here is the first application that we're looking at is of construction use, and it is a arch bridge based on a parabola. So you need to, if you have some kind of construction that I've given you, you need to look and see, is this a piece of an ellipse, like here? Is it a piece of a parabola, like here? Is it a piece of a hyperbola? Because the formula that you would use for construction will be very different based on that. So the first one says an arch in the shape of a parabola has the dimensions shown in the figure. How wide is the arch? 9 feet up. We're going to do the same thing we did in this example. Is first we're going to come up with an equation that we can use that describes this. And second, then we're going to answer the question. Now, I did this one a couple of different ways. The first time I did this, I decided to make the, what did I do here? Oh, I decided to make this vertex the origin, 0, 0. And then the second time I did it, I decided to make this point right here the origin, 0, 0. It works either way, but I think what was a little bit easier was this, because then we don't have to deal with negative. So I'm going to choose to do that. We get the choice of picking how we want to apply our axis that we want to throw on here. So I'm going to apply my axis so that this is my XY axis and this is the origin. Okay, so if this is the origin, then this is still the vertex, but the coordinates of my vertex will be 0, 12. And this is my H and this is my K. Okay, this is a parabola, so let's remember, what does a parabola look like? It's x squared is 4cy, or y squared is 4cx, or x minus h squared is 4c times y minus k, or y minus k squared is 4c times x minus h. Okay, so since this one is facing up and down, I'm going to use the formulas that face up and down. When I chose to let the vertex be 0, 0, and this point would be 0, negative 12, then I use this formula. But that's not what I'm doing this time. I'm letting the vertex be at 0, 12, so I have a H and a K. This is the formula I will be using. So, we know what H is, we know what K is. So let's just write that. X minus 0 is going to be x squared is equal to 4 times c times y minus 12. That's what I know so far. Once I solve for c, I have an equation. I have a working equation for this guy. I need just a little more information, and it's here for me to pull off of this. Let's pick a point that we can identify the coordinates of a point, and this is one right here, and this is another one. We could use either one of these. The coordinates of this point are x is 6, y is 0. The coordinates of this point are x is negative 6, y is 0. We can plug in either one of these into this formula and solve for c. Then we have a working equation of our parabola. So let's do that. I'm going to plug in this one because it's positive. Okay, x squared, 6 squared, is equal to 4 times c times y, 0 minus 12. So 36 is equal to 4 times c times negative 12. 36 is negative 48c. I can solve for c by dividing both sides by negative 48. And so c is going to be negative 36 over 48, and you can simplify that to negative 3/4. Okay, that is the value of c. Okay, let's write our formula. X squared is equal to 4 times negative 3 over 4, which is c, times y minus 12. Those 4's will cancel, so we get x squared is negative 3 times y minus 12. This is the equation that describes this arch brick. Now there was a question they asked us, which said, how wide is the arch 9 feet up? All right, so this is, from here to here is 12, right? So if I go up 9 feet, let's say, they want to know how wide is this. So if here's a point, right? We know that the y value for this is 9. We went 9 feet up. What in the world is x? That's what we got to figure out. So we have an equation that describes every point on this parabola, and we need to know x. So let's plug in 9 for y and solve for x. So let's do that. This is my equation. Let me make just a little more room here because I got it kind of sloppy. Alrighty. Okay. I'm going to plug in 9 for y. So I have x squared is equal to negative 3 times 9 minus 12. X squared is negative 3 times negative 3. X squared is 9. X is plus or minus 3. This describes this point, 3, 9, and this point, negative 3, 9. Let's answer the question. How wide is the arch 9 feet up? Well, the arch is 3 plus 3, or 6 feet wide, 9 feet up. And that's how we can do that one. All right.